Okay, so in continuation then, that answer would then be 6 plus 9, which would be then 15 halves. So the important thing here again is that when you have a constant, you have to split it up. This is not the graph of 1 minus f of x. You just can't use that graph for the whole function, for the whole integrand. Split it up at the constant, do this separately, then do that piece. And any area that's below the x-axis is negative. Okay? And also, if we had anything like this, if I go from negative 2 to 0 of, say, 2 times f of x dx, well, obviously it's just a constant. And as before, we could pull the constant out in front and do 2 times negative 2 to 0 of f of x dx. And then this area is above the x-axis, so that would be then 1/2 times 2 times 3, so that would then give me a value of 6. Okay? Okay, another important property is if we have, suppose I have 0 to negative 2 of f of x dx. Notice here in this example, I'm integrating differently. I'm integrating from a higher number to a lower number, from 0 to negative 2, which means now my difference in my x's is going to be negative, because the x's are decreasing from 0 to negative 2. So therefore, this, what we can do is, we can switch the limits of integration. And when we switch the limits of integration, we switch the sign. So then now this will come from, or go from negative 2 to 0 of f of x dx. Okay, so if you look at all the problems we've done so far, we have always integrated from a lower number to a higher number. Well, what if we had the higher number down here and a lower number up here? Then that means the x's are decreasing, so your delta x is technically negative, which will be brought out here in front then. So what you can do is, when you switch the limits of integration, you also switch the sign. So then that would become a negative now. And I'll talk to you more about that in class. So this would be a negative times whatever this area is. Well, since this area is above the x-axis, it'll be positive. So it'd be 1/2 times the base, which is 2, times the height, which is 3, which would then be negative 3. So then that would be then negative 3 overall. And you think, well, wait a minute, it's above the x-axis. It's above the x-axis and it's originally positive, but because we were integrating from a higher number, 0, to a lower number, then that value gets assigned a negative. Now over here, if we were to integrate, say, from 6 to 3 of f of x dx, well, because we're integrating from a higher to a lower number, then that answer would be assigned a negative. But because we're below the x-axis, that area is already negative, so a negative times a negative would be then a positive. What you can do is, to get used to integrating, it's always better to integrate from a lower to a higher number, is just when you switch the limits of integration, you negate the sign. So it'd be the negative times the definite integral from 3 to 6 of f of x dx. Okay, and just 2 more parts. Next, if you're given that f is continuous on a closed interval, so f is continuous on a closed interval negative 8 to 8, and the definite integral from 0 to 8 of f of x dx is equal to 4. Find these values. So from 0 to 8 of the quantity f of x plus 2 dx, what I would just do is split it up at the plus sign. Go from 0 to 8 of f of x dx plus the definite integral from 0 to 8 of 2 dx. So this answer is given to you as 4. So it'd be 4 plus, this is of a constant, times the upper limit minus the lower limit. And 2 plus 4 is 16, plus 4 is 20. Next, if we add the definite integral from negative 1 to 7 of f of x minus 1 dx. So then u would be equal to x minus 1. If you have anything going on the inside of the function, you're going to have to do u substitution. Something's going on the inside here, so you're going to have to do a u substitution. So u is equal to x minus 1, du is equal to dx. This becomes a du, this becomes your u. Now these have to change because these are in terms of x's. So then now this would become, this should have been plus 1. Plus 1. Sorry about that. That should have been a plus 1. So then u equals x plus 1, du equals dx. If x is negative 1, negative 1 plus 1 is 0. And then when x is 7, 7 plus 1 is 8. So we end up with 0 to 8 of f at u du, which would then be equal to still 4. As long enough the limits of integration change accordingly, this will have the same value whether it's in terms of u or x. Next, what if we are told, let's be given this one, 0 to 16 of f of x over 2 dx. So again, if you have stuff going on here on the inside, choose u to be x over 2. du is equal to 1/2 dx. Put a 1/2 in, take out a 2. This here will become your du. That becomes your u. These have to get put in for x. So 0 over 2 is 0. That'll stay as 0. But 16 over 2 will become your 8. So this now becomes 2 times the definite integral from 0 to 8 of f at u du. So from 0 to 8 of f at u du, this becomes 4 times 2 is 8. Again, if you have stuff going on the inside of the parentheses, let u be equal to the inside, take the derivative of both sides, and work it just as we did before. But the important thing is that these limits are in terms of x. They've got to change in terms of u now. Another one, suppose we are told that from negative 8 to 8 of f of x dx, we're to find that value, but this time f is an even function. So if f is even, then that means we've got y-axis symmetry. So the y-axis is cutting the areas into 2 equal parts. So from negative 8 to 0 of f of x dx plus 0 to 8 of f of x dx. So each of these areas would be the same. So 4 plus 4 would then be 8. If we were told that this was an odd function, then that means it's got origin symmetry. So that means it's like a picture like this, like x cubed, where you got the same area above, bounded by the x-axis, as you got below the x-axis. Well, because this is a positive area and this is a negative area, when we would go, say, from negative 8 to 8, that answer would be 0. So if this is odd, then from negative 8 to 8 would be equal to 0. And just one more. Suppose you were given the definite integral from 0 to 8 of 3 minus f of x dx. If you see the minus sign, split it up at the minus sign or the plus sign, so it would be the definite integral from 0 to 8 of 3 dx minus 0 to 8 of f of x dx. So this answer would be the constant times the upper minus the lower, which would be 24. This answer is given to us as 4, and 24 minus 4 is 20. Okay? And just one quick problem to talk you through there that comes up in the homework is if you're given a velocity graph of time versus velocity, and it looks like this, say, for example, and just suppose this here is 1, 2, 3, 4, and we are to calculate or approximate the distance traveled from one time to another time, or maybe find the total distance traveled from 0 to 4. First of all, why is this distance underneath this graph? Well, if you're given velocity, the area underneath it would be represented as the definite integral from 0 to 4 of v at t dt. Well, suppose velocity is measured in meters per second and time is measured in seconds. When you multiply the units in the integrand, the seconds would drop out and you're left with meters, which is distance. So how can I approximate maybe the total distance traveled from 0 to 4? Find the area underneath it. Well, you can either do a left, a right, or a midpoint approximation, or even use trapezoids. So just suppose this here was a y value of 1, 1, and maybe this here is like 2, 3, and this here is like 3, 5, and just suppose this is here 4, 7, just something like that. I'd rather choose a square root. Looks like a square root function, but just to throw these numbers out there, to approximate this using a left Riemann sum, I want to use the left endpoints. So if these are my subintervals from 0 to 1, and then from 1 to 2, and then from 2 to 3, and 3 to 4, I'd want to make rectangles where the left endpoint is on the curve. So I'm going to use the left endpoints. So my subintervals are 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Okay? So then that means the width of each of these is 1. So using a left rectangular approximation, delta x is 1 in each case. And then I want to take the left endpoint and get that y value. Well, I don't have a function v at t equals something. I have a graph. So I want the y point when x is 0. So that's going to be 0. And then when x is 1, just suppose y is 1, which it would really not be in this case because this is like something linear. And I just didn't draw it linear, but it could be linear. And then when x is 2, y is 3. And then when x is 3, y is 5. So these correspond to the y values at each of the x's that are the left endpoints. And since I don't have a function to retrieve the y value has to come off the graph. So you just add these and get 8, and 1 is 9 times 1 is 9. If you want to do a right rectangular approximation, so then it's 1, delta x is the same. And by the way, in the future, these will not always be equal subintervals. So this only works conveniently when they're equal size subintervals, all a width of 1. But when they're not equal subintervals, how will I do it? Well, I'll have to find the area of each rectangle individually and then add them up. This only works, again, conveniently when delta x is the same for each subinterval. So if I take 1, put it in, I get 1. I'm taking the right endpoints now, so I'll box these. So when x is 1, y is 1. When x is 2, y is 3. And when x is 1, 2, now I'm at 3. When x is 3, y is 5. And now I'm at 4. When x is 4, y is 7. So then I'll get here 6, 4 that is, and 5 is 9, plus 7 is what then? 16. So pretty big over approximation as well as maybe under. If I take the two and add them, it would give me a pretty good answer to what the midpoint would be around. So a graph of this, if I create rectangles where the first one, the left, is on the curve, between these two, draw it to the curve up and over. This left endpoint, draw it to the curve up and over. This endpoint, draw it up to the curve up and over. So you could definitely see that the left approximation under-approximates it. Now the right. So over to the right, up, this way. To the right endpoint, this is the subinterval. To that right endpoint, up to the curve, there it is. This point will not be on the curve. Over to the right, up to the curve, over and down. This endpoint will not be on the curve. Over, up to the curve for the right endpoint, over and down. This one will not be on the curve, so that's the over approximation. So again, that's how I could approximate the total distance traveled from 0 to 4. You can also sometimes create trapezoids. You can go like this and create trapezoids, which you can improve upon our approximations. So the area of a trapezoid is 1/2 here in this case, if this is the trapezoid, just for example, right here, my parallel sides are my bases. So my height would be 1 unit long, and suppose my base here is 1 unit high, and my base here is 3. So that's 4 times a half, or 2. So this trapezoid would be 2. And then I could find the area of this trapezoid, which would be 1/2. This here is 1, and this here is 3, and this one here would be 5. And half of 8 is 4. Okay, and then this right here I could create is just a triangle. So then that there would be 1/2 times the base, which is 1, times the height, which is 1, so that would be a half. And then I can do one right here. So that would be then 1/2 times, again, the height is 1, this base, this trapezoid right here. These are my bases. That base is 5 units high, and this one is 7 units high. Half of 12 is 6. So then just add them up. What do I get? 6 and 4 is 10, and 2 is 12. 12.5 I get. And notice that's not too bad, because I take 16 plus 9 is 25, divided by 2 is 12.5. So pretty good approximation, creating the trapezoids here and the triangle here, and adding them all up. And again, why does it give us distance? Because the area under velocity gives us distance. And how do I know that? Well, if I take the definite integral from 0 to 4 of v at t dt and multiply these units, the answer is meters, which would be distance.